Okay, all right. So we had a few examples of what of a differential equation. No, not differential equation, but the settings are that that ultimately are differential equations, but the end result doesn't have to be. So once again, solving a system of equations that is straight uniform speed, constant speed, or constant acceleration, as this example of. And we introduced the vectors independently, and then we introduced parameter curves. So that's the main topic really for the very last part of the last topic for the test is really parameter curves. And so some of the parameter curves could look like this. Okay, so the acceleration is constant, and the whole algebra that though the formula is written in familiar terms looks very familiar, like those solutions for free fall. But this time, these are a bunch of vectors. Okay, so P is a vector, P naught is the vector, your initial location, V naught is the initial velocity, A is the acceleration, which does not have to be constant. It does not have to be the same in all directions. Okay, so in fact, you can easily redo this for dimension 3. This is all has been dimension 2 for dimension 3, and then the force, the acceleration is only 1 in the down direction is non-zero, in the other 3 directions it is. Okay, so and then if you decide that it's not the way it is, and maybe you want to have acceleration that are pushing up, it's the same thing. Okay, so but otherwise it was a study of and a review of parameter curves, and so important now straight line representation of parameter curve that is a straight line, parabolic motion and a parabola. This is going to be a parabola, and then and thirdly is rotational motion. Okay, so these are the 3 motions that we know apart from differential equations. So is that it? Obviously it is not, and then we're looking for to start with this tool, parameter curves. We want to rebuild the same theory from scratch as we did in dimension 1 from the day 1. Okay, so the once again reviewing what we have had is initial value problems. In this case, as you can see, the first one is for the difference equation, which produces. We go on from it with the Euler's method, and the second one after the limit we have derivatives, and then in hope that maybe we can actually figure out what the answer is exactly. Okay, so what if there are 2 variables? Okay, so the time t remains the same. We're looking at phenomena when there are 2 quantities that depend on time vary. Okay, so that's the example we just looked at is free fall with x and y are those 2 variables, horizontal vertical location, both depend on time. And this is the good news, is that the motion is the key to solving the problem, is understand that there's a wall between the 2. Entirely the horizontal component has nothing to do with the vertical component, and then the vertical component is free fall. As you can see, that negative gt is the term that creates acceleration in a downward direction, and the horizontal there is nothing, so it's a constant velocity, and so that's all there is really. And then so like I said, I try to put a wall here, suggest that this is a wall between the 2, and then you don't really need to do anything beyond what we have done before. It is a 2 one-dimensional problems, and they solve separately as we done just last time. Okay, so and then what if, however, the velocity in the horizontal direction depends not only where you are horizontally but also where you are vertically. Okay, so if it makes sense. So so horizontally, where you are, maybe I don't know, or how should it? Maybe this one over here. Okay, so the wider the vertical speed, we're not doing acceleration here. So the vertical velocity, okay, dy dt depends on naturally your where you are in the vertical direction. But what if we also throw in x here? Okay, is it possible to throw in an x here? So the dy dt, the vertical velocity, depends on x. Well, maybe the wind is blowing, but it is slowing down as you move in the x direction. Actually, it becomes not blowing as fast as in the beginning. Okay, so the winds, and naturally, if you look at the map, the velocity is different in different locations. So what if that is the case? And then the idea of having a wall between the 2 disappears, and we have to deal with the right-hand side, all of these things right here, depend on both x and y. So roughly here, as you can see, dx dt depends on x. It is autonomous differential equation with respect to x. dy dt is h of y. Once again, autonomous differential equation with respect to y. And then solved entirely differently, and then they bring them together if necessary. So, but what if this is what we have? As you can see, g of x, y, and so your rate of change of x depends on y, and rate of y depends on x. That's a possibility. So you can make up, as I just tried a second ago, tried to come up with an example when the motion, your horizontal motion depends on the vertical location, or your vertical motion depends, or velocity depends on your horizontal location. And so it's totally possible to come up, but there is something more interesting, and that's the predator-prey model. Okay, so when there is an interaction between x and y, so there are two quantities, rabbits and foxes. And then naturally, the number of foxes affects the number of rabbits, and vice versa. Okay, so that blows out of the water the idea that we can solve two differential equations entirely separately. So we're going to know the rate of change of the rabbits, the rate of change of foxes, both with respect to time, but it depends on the rate of change, the rate of, say, growth of the number of foxes will depend on the number of rabbits. Okay, so that's the dependence right there in the very beginning. Okay, so let's go with this. In the case of an unrestricted population growth, when there is no dependence, the foxes are living by themselves, and we don't know what they eat, and so they just grow exponentially or decay if they don't have enough food. Okay. Similarly for the rabbits, if we don't care about the foxes, they grow in number if for as long as they have food. If not, they decay exponentially. So the underlying solutions are familiar. Okay, so when the x and y are independent, we have these two possibilities. It's pretty much the same possibility, exponential model of population growth. But the reality is this. So the relation, if we want to just on the surface see what the relation is, the number of okay, so this is the wall once again. What's in the line in the middle is the wall. So if there is enough food, then the rabbits are growing exponentially with no foxes. If there are no, but if we assume that foxes eat rabbits, but there are no rabbits, as the number of rabbits declines, there is not enough food, and there is decline in the population of foxes. So these are two underlying types of dynamics that we face. Now, and we can write them as we have with the same differential equation, dc dt is equal to kc, depending on the value of k, either we have growth or decay. So we know that there will be something exponential about it behind the whole thing, but it's not going to be as simple as this. It's certainly not separated into two different things. So we start with the rabbits. So two factors affect their population. We assume that they have, once, just like in the picture on the left, we assume that there is an unlimited supply of food. There is an unlimited amount of food. Okay, so on one hand, on the other hand, so they reproduce and grow exponentially, would they, if not for the predator? And this is the rule that dictates the interaction of the rabbits with the foxes. The gain of the rabbit population per unit of time through their natural reproduction is proportional to the size of their current population. So we already know that. And then, so that's the component to the rabbit's gain, and that's they only gain. They eat grass, presumably, and then there's enough grass there, and so that's the model that we have written before. Okay, so alpha, some coefficient, maybe large, maybe small, depending on how well they live, and then multiplied by the current population and the proportion to the time. Okay. So proportional to the number of rabbits in the first place and proportional to the length of time. Okay, so we do not try to divide by, this is the delta R, say, right? So R stands for rabbits, but we don't try to divide and go with derivative right away because there is a second component we have to take care of first, and this is what it is. The foxes are being introduced into this model, and they bring the number of rabbits down. Okay, so the green one is no foxes, and the blue one is when there are enough. If one fox, it won't make any difference. But if the number of foxes grows at some level, they start to dampen the growth of the population of foxes and maybe entirely diminish it. So we don't know. Really. We just know that it might possibly go down. That's what the picture on the right indicates. The foxes bring the population of rabbits down. Okay. So if we want to make it more specific, proportionalities, once again, is what we're after. We don't try to come up with fancy formulas, just start with a simple situation. So the rate of predation upon rabbits is proportional to what? Okay, rate of predation, in other words, how many rabbits have been eaten per a period of time. Naturally, it's proportional to the time, but also to what? To the likelihood of that a rabbit meets the fox. And in other words, it is proportional to the number of rabbits and the number of foxes. Okay, so naturally, the more rabbits. If you double the number of foxes to begin with, then there will be twice as many rabbits eaten. Okay, because it's a probability. If they meet in the forest, the rabbit is eaten. Okay, but it's also proportional to the number of rabbits in the first place. So if you have a double number of rabbits, they will be eaten more. Okay, naturally, it still will be the what's at the top there is still in height. And so the more rabbits, they will be reproduced faster. But nonetheless, this is the other coefficient that, or rather a term that affects the number of rabbits is this. So once again, proportion to the rate at which rabbits and foxes meet. Okay, and that is proportional to the sizes of the population x and y. So it becomes instantly non-linear. Okay, this is non-linear. Okay, even though x is linear and y is linear, but we multiply them together, so x, y is not linear. Okay, so these are the two coefficients, two terms, and this if we add them together, so this is the beta is just some coefficients that depends on the situation, and it to be established to be determined by pretty much observation. Okay, so that's the effect. R stands for rabbits. X is number of rabbits. Delta X the change in number of rabbits, and it is, as you can see, the first term is the natural growth from eating grass, and the second one is what brings down their number by the presence of Y, which is the number of foxes. You can see that if here I put a y equal to 0, then the second term disappears, and we are in the same place as before, and rabbits are growing in succession. Okay, so alpha naturally assumed to be positive, so beta is positive. Okay, now we flip it. Okay, and foxes are they only eat rabbits, they only eat grass. Okay, so then we speak of the loss of foxes population. And they lost per unit of time through their natural death, proportionally to the size of the current population. Okay, so once again, the same model, except the exponential growth and exponential decay are opposite of each other, but it's basically the same story. So once again, I have a gamma, and that gamma is positive, and the loss, so it will be coming up with a negative term proportional to y once again. So and now we introduce rabbits. Now the foxes have something to eat, and therefore it's possible if you have enough rabbits that the population actually stop to decay and start to grow. Okay, so that's what rabbits do to the foxes. So once again, the contribution is separate, but it's similar to this one. Okay, so that second term right here. So rabbits' loss is fox's gain. Okay, so it's once again proportional to the same three values, x, y, and delta t, proportional to the time, how many foxes, and how many rabbits. Except the contribution to the growth of the population might not necessarily be exactly the same. So I have an extra coefficient here, which is delta. Okay, so fox's gain is delta times x times y times delta t. So that's the whole story about the foxes, but once again, you cannot look at it separately because x is present in the first term, and the population of foxes depends on the population of rabbits, that's x. And once again, if I put x there equal to 0, no rabbits, and then I have the exponential decay model with one term. So they cannot be uncoupled. because rabbits are eaten by foxes, and the more foxes, the more rabbits are eaten, and so it goes back and forth. It cannot be eliminated unless from the beginning, if you assume that from the beginning there are no foxes or there are no rabbits, then you can otherwise they always coexist. That's the thing about it. Even though you can imagine hypothetically that there are so many foxes that they eat those rabbits so fast that they disappear, and after which the foxes disappear too because there's no food left. So it's possible, but we'll see how it works out. Okay, so the discrete model is on the left. Okay, so I factor delta t out. Everything is proportional to delta t the time. Very convenient. On the left, I write two different difference equations for x and y separately. On the right, I put them together into one vector form. As you can see, I not only I factored delta t out, I also factored. No, there's no x there. That's a typo here. Okay, so and then you can put it in the form of a vector with delta t being a coefficient. Okay, so this is sufficient for us to write recursive formulas. Okay, so the right-hand side is there. So xn, once again, this coefficient, you can still remember where it comes from, even though right now we're not concerned with it. If xn, yn is known, the current population of rabbits, current population of foxes, if these two numbers are known, then we can, through this little computation, find the new populations, xn plus 1, yn plus 1. Just the way we did it before, except it's not one number, it progresses on and on, it's two numbers. So there will be two columns, one for x and one for y. Like this. Okay, so either you think about two separate populations affecting each other, or you think about it as a point on the plane. Okay, so that's the dynamic. So there will be motion through space of data, pretty much. So it's not a physical space. It's there are two coordinates, one for foxes, the other one for rabbits, and we are moving through that space with time. That's a typical situation. So I translate these two formulas into my spreadsheet right here. Just to run before getting deeper into that, let's run a simulation. So once again, this is nothing special about it. These are just these formulas, even though they look kind of odd. But once again, and we go one row at a time to compute the next row, two columns at a time. One row going down further and further, and using only the first two entries right above it. And so we're going down until we compute as many as necessary. And once again, it's a spreadsheet. That's how it operates. Okay, so here it is. Okay, so here I ignore the ideas that we have had. For now, let's just do them separately and see if it reveals anything. So the computation I described is on the left. So time does not come into play, just a marker. Okay, x and y are, so we started with 10 rabbits and 5 foxes. Okay, with some coefficients are also been chosen, alpha, beta, gamma, and delta, right there at the top. And somewhere delta th is also chosen to be 0.2. Okay, so we plug into this formula. This is I believe this is my delta t or h. Okay, and then as you can see, I plot x's against time, rabbits, and I plot y's against time. Okay, that's for the foxes. So you can see what has happened. It kind of happened what I just described, right? So you see how do you read these graphs?
Out really quickly.
Yeah, but in the beginning there were enough of them, so much so that the foxes actually went up at first. But then there's so few rabbits left that it's not enough for the foxes to eat, and then they start declining on and on. You can try to predict long term. What do you expect long term is going to happen? Maybe they'll recover. Maybe this number of foxes is so low that the rabbits start to recover. It's possible, right? So we'll see. But before we do that, let's bring these two together. Especially, it's so easy, right? So a column of numbers plotted in the first one, the other column is plotted in the second one. If we combine x and y together, This is the x and y for rabbits and for foxes, and plot them in this fashion on the xy plane. So that's the behavior, one single graph that captures the whole information from those graphs on the left. And so we're moving through horizontal axis is the rabbits, and vertical is the foxes. And so indeed there is a decline of rabbits, growth for a short while of the foxes, and then it drops. The foxes going down really fast because there's virtually no rabbits left. And then it appears that it does go towards zero, but we cannot be sure because they never, unlike the actual rabbits foxes where you cannot have less than one rabbit. Here it is more hypothetical, so you can actually have a hypothetical very small number of rabbits with less than one. Okay, but the key observation here is that what the answer is a parametric curve. So that's why we study parametric curves for exactly this purpose. So that we can imagine it, we can visualize in the lower dimension, we can visualize on a piece of paper that kind of dynamics. Okay, so another experiment here. So I changed the values of alpha and beta. Okay. And change h slightly. So h might also be h. Remember what h is delta t. It gives you the quality of our approximation. The larger h is, the worse our approximation. You can see how fast they're moving. So here's another model. Here's the longer simulation. So we start in the middle over there, and then we started with what we just saw. Slight growth of foxes with a fast decline of rabbits, and then when both of them are small and they drop towards the corner, what's that corner? It's 0, 0. That corner, left bottom corner is both of them are close to 0. But as you can see, they did not die out all. Okay, so they actually yeah, you can see the arrows. Can you see the arrows, right? So the arrow moving in a manner that is counterclockwise, and even though we were very close to the y-axis, then we're very close to the x-axis. Nonetheless, we did not die. We went on and make a full circle and come to almost the same place as before, but there with more larger numbers. But then we repeated the same thing happened, meaning that once again, too many foxes eat too many rabbits. Rabbits die out, and then not enough food for foxes, and then foxes die out too. But once again, you can see if you look at the very bottom, have they died out entirely? So, well, apparently not, because the number of foxes seems to be 0, and in the meantime, the rabbits are actually growing, right? So you can see that at the bottom, we are going along the x-axis, so it appears that the rabbits have not died out entirely, and which means that maybe foxes haven't died out either. Okay, so maybe if it's a fraction of foxes left there, with plenty of food, might recover. So it seems to be spiraling out like this. Is it really spiral or not? The simulation does not tell us, because it definitely does show spiraling, but you cannot tell. Okay, so once again, I take the limit. That is my differential equation, system of differential equations. So derivative of x depends on x and y. Derivative of y depends on x and y too. Okay, so none of the methods that I have had would solve this differential equation. It's called the Lotka-Volterra equations. One of the first systems of differential equations that were beyond just motion. So, okay, it approximates the discrete model, and the number of foxes is not discrete anymore, so it can go proportionally to, it could be fractional, anything less than 1/10 of a rabbit. So you can, when you see a fractional number of items or a fractional number of rabbits, foxes in this thing, you can just say that maybe it's the probability. You don't know how many of them there are, but those fractional numbers simply reflects the probability of seeing it in the forest, and those are really the numbers that are part of the model, the likelihood of meeting for a fox to meet a rabbit and vice versa. So it's not that weird. Okay, so we have equation. We started with model. We wrote the differential equation for it. We did one simulation just to see if it Makes sense, it does. And now we'll call if analysis the next stage of analysis. So very similarly to dimension one. Monotonicity is very, let's do monotonicity. Okay, so when the one number is increasing, when decreasing, so this monotonicity of a differential equation of one variable is this. So whenever from short time ago, wherever the right hand side of my one-dimensional differential equation is positive, the solution is increasing, and where it's negative is decreasing. That's the whole, almost the whole story of qualitative analysis. Okay, so now we're looking at if we were to switch to a differential equation that is autonomous. What does it mean? It means that there is no y to worry. There's no t to worry about. There's only y left. In which case the statement still holds. So this still holds, but you might pay attention more on this, on the stationary points. Remember we did that. Stationary points is where things are interesting. In the vicinity of a stationary point, things are interesting. Otherwise, the behavior is generic, which is what the first theorem says. So let's see. Can we have similar statements made about our differential equations? Yes, we can. And so except we have two functions, therefore both of them may be increasing or decreasing, which means that instead of two cases that we have here, there will be four. Okay, so once again, decreasing, and vice versa. So then we were doing sign analysis of our right-hand side functions. These are the right-hand side functions, and they could be once again plus minus, and so there are four possibilities. Okay, so for example, plus plus. If it is plus plus, we are going like this. Okay, plus plus, x and y increasing. Therefore, we're going in the direction towards what you call northeast, right? Okay, so let's do that. Once again, this is my these are my right hand sides, and let's take a look at them. But once again, remember we did the same story with one-dimensional case. These are why these points are important with derivative is equal to 0, because that's where the behavior change or might change. So this is way more complicated because they are two variables, but nonetheless we are looking at where the derivative of x is equal to 0 and the derivative of y is equal to 0. Okay, so starting with x means what x prime is equal to 0. What does it mean? That's right. So there's no change. It could be maximum or minimum, but technically there is no the growth or decay of rabbit's head is stalled. Okay, that's what it's supposed to mean. So there might be a change. So it was, for example, it was growing and now it stopped and might go down, or it might continue on. We don't know, but surely it will not reverse itself unless it hits this point. So x prime equal to 0 is important, and then that's the where we look at them. Then this is the x prime is equal to first equation. X prime is this. So that's what we will have to examine in order to determine where there are these reversal points. So this is a reversal potential. I put a reversal. It doesn't have to be a reversal, but we know that if there is a reversal, that's where it is. So alpha x minus beta xy equal to 0 is where these points lie. Okay, it's a relation on the plane, a very simple relation, and we need to plot it. Okay, so we need to plot all xy's, points xy on the plane, where this is true. Remembering once again, alpha and beta are positive. It's not complicated. We factor it out. Okay, x factors out. Okay, so all right. So what's the conclusion? So an algebraic question. X times alpha minus beta y equal to 0. What can we say about the graph? What xy's satisfy this equation? What's the importance? So we factored. Why did we factor? Two things multiplied by each other equal to 0. What's the conclusion?
X is 0 or 1, y is.
Well, yeah, so either one factor or the other must be equal to 0. If neither one is equal to 0, you cannot have 0. So one, at least one of the two must be equal to 0. And indeed, the simplest case is x equal to 0. And what is x equal to 0 if not no rabbits, right? X equal to 0, no rabbits. So that is a special place, and not very interesting place, but nonetheless worth mentioning that x equal to 0 is the possibility of where the universal nothing is happening naturally. So x equal to 0, which means that the rabbits are dying, and then what is happening to the I'm sorry, foxes are dying and rabbits are already dead. Okay, so that's not an interesting part, but nonetheless, the second part, if I take the second factor, there is a special number. Look at it. There is a special number of foxes. Why is it foxes? There's a special number of foxes where the effect on the rabbits is the reversal. Okay, so either from decreasing to increasing or vice versa. We don't know yet, but that's a very important point. Y equal alpha over beta, that positive number of foxes will produce this effect. Okay, so that's the that's what we have produced, and the in that case, as you can see, we actually can if we accept that as the given x equal to 0. So that's we're looking at the two cases separately. So this case is here, x equal to 0. We end up with we're back, right? So this is the back. The story, not an interesting part of the story. It is when there are no rabbits. Okay, so and then as you can see, as we already predicted, the population of foxes decays to 0, and that's at the bottom here, right? That's the decay. So that's a trivial case, not very interesting. So we're looking at the second one, this one. Okay, the second case. So case 1. This is case 1, and now we're going to case 2 with the not equal to 0. So there are both. We are not saying anything about rabbits, by the way. That's the only statement that we made of is about y the foxes. Okay, so like this. Okay, so y equal alpha over beta is actually a straight line, horizontal line through the in our plane. Okay, x equals 0 on the left, by the way, that's the decay that we just solved the problem. That's case 1 here. This is case 1, and this is case 2. And then that special point is that line can be only crossed in the vertical fashion. So it cannot cross like this because x prime equal to 0. So x prime equal to 0, which is what the starting point is, means this on the xy plane. Well, horizontal x prime equal to 0 means my parametric curve goes like this. So it crosses, it might do it this way or that way, but it cannot cross in an angle other than in the vertical direction. Okay, that's what this picture shows. So all the trajectories, all the parametric curves that support the solutions have to cross this line in the vertical map. Okay, so that's all we have found so far. But that's just the beginning. And that's where the reversal might be. So the reversal, as you can see, depending on which of these, there are 4 possibilities still. The reversal might appear or not, we don't know yet. To find out, now we look at the signs. Okay, so that's where the thing is equal to 0. Now, where is x prime equal to 0? Under what circumstances there is a growth of the rabbits? X prime positive 0. We know where it is equal to 0, and now we solve the equation. It turns out it is when y is less than alpha over beta. In other words, below that line. So below that line, there aren't too many foxes to bring the number of rabbits down. Okay. Right, so x prime is the rate of change of the rabbits, and then we found out that this area is right here, this area below the line. So this is a good area for the rabbits. Maybe it's not growing fast, but it certainly is not going to be declining. Okay, so it will be on the line. It's constant, sort of. On the below it there will be growth. Okay, so if we were, do I have this picture here? If we were to do it in the manner that I did before, then this is how I would do it, like this. So rabbits, the number of rabbits are growing. like this. And that ignores the question about what happens to the foxes. But this is what we know about the rabbits, that they will be growing. Okay. In the meantime, you can guess that over here it will be the opposite. X's are negative. X prime is negative here. X prime is positive there. X prime is equal to 0 on that line. So roughly that's the horizontal, the x dimension of our dynamics will be growth, decline. Okay. Too many foxes. If we go beyond that green line, there are too many foxes, and they bring the number of rabbits down. Okay, that's here it is. Fewer foxes, good growth, or some growth. Too many foxes for any growth, and it declines actually. Okay, so we were not describing in what exact manner it is declining, but it is declining. Okay, so x prime is the rabbit. So the conclusions are made about the rabbits, but they are on the xy plane, which means that indirectly foxes play a role. But it is indeed the dividing line. That's the number of rabbits is frozen is when y is equal to alpha. Okay, so that's not enough, obviously. So we go to the second equation and examine y's, how in this exactly similar fashion, we look at now at the foxes. Y prime is equal to 0 when there is this freezing of the number of the rabbits. We solve it in a similar fashion. Once again, the right-hand side of my differential equation is this. We set it equal to 0 with factor. Once again, there are two possibilities. Y is equal to 0 or x is equal to gamma over delta. The left one is the trivial case when there are no foxes. When there are no foxes, what happens to the foxes? They cannot just spring from nothing, so they will remain 0. So there's nothing interesting happening there. So that's and in the meantime, so that's what's happening here. So we're back to the trivial case, one-dimensional case, and then what happens to the rabbits? X they grow exponentially. Okay, so that's what has been solved. Case 1, case 2. Now we go in with case 2. There's a special number of rabbits that freezes the number of foxes. In other words, so with when the number of foxes is like just exactly this, the number of rabbits is exactly this, then the number of foxes neither growing nor declining. Okay. So once again, is it helpful? Maybe not, but if we are collecting data little by little, and that's what we have collected from the second part of the analysis, is there's a vertical line now, the line being that one, x is gamma over delta, and that line separates the behavior of foxes, of different types of behavior of foxes, once again decline, increase or decrease. So when there are, it depends on the rabbits. When there are many rabbits, there will be growth of foxes. When there are too few rabbits, there will be decline of foxes. Okay, so this is here it is. Once again, where y prime is positive, will be y prime positive to the right of this line, the green line, and it's negative to the left. Okay, so that's the answer. Once again, you have the arrow indicating the growth of foxes and decline over there. Okay, so you can guess what happens next. What's next? Put them together, right? So we have totally unrelated, seemingly unrelated behaviors that we discovered about foxes and rabbits, depending on where that we are, where they are, x, y is. And there are then 4 sectors. So 2 and 2, 2 this way, 2 that way, we have 4 sectors. Okay, so like this. And here's an interesting picture, right? So so as you can see, once again, below the line, everything goes to the right, and above to the left. And to the left of that vertical line, everything will be going down, and to the right it's up. So when you collect that information, once again, the information is actually hidden here, for example, here. Okay, x prime is positive, so that's where your skills with parametric curves are important. X prime is less than 0. So let me do it for you once. So x prime is negative, means that this is what we're seeing. Y prime is positive, means that we are seeing that. Okay, and if we combine these two together, we're seeing this. Okay, that's the derivative of parametric curves. Looked at their signs separately. Okay, combined together, when they're known, we can know which way roughly the curve is going. And so in this case, it's going, if that's appropriate, it will go very approximately, but it is northwest. Okay. So one positive, one negative, and it goes in that direction. Or here, both of them positive. Remember this one, both of them positive, and then it goes to northeast. Okay, so once again, everything, it's very simplified picture, just the way we did before. So very crude pictures, making sure that we're crossing those two lines appropriately in a horizontal fashion for the vertical line and vertical fashion for the horizontal line. And then in each of these four sectors, we also know roughly where we're supposed to go. So that's really not much of a picture, but you can tell that you can try to make a prediction because it looks cyclical. At least the impression that you might get from these pictures that they kind of are cyclical. What would make it non-cyclical? Right. The spirals in or out. But the point is that it's misleading picture because I drew all the arrows of the same size in the same direction. But we don't know that. In fact, we know that there is no symmetry there because it's infinite in that direction and not infinite if you go down or up. Okay, so infinite up and right, not infinite left and down. Okay, so there is no symmetry. There cannot be no symmetry. So then it is suggestive by the picture that it must be rotating only because of this crude approximation. So best you can tell that it might be spiraling, but probably what it is not doing, and so it might be spiraling in, or it might be spiraling out, or maybe it still might be cyclical. Okay. So, well, probably worth mentioning the central point. It is there. That's also part of the whole diff analysis, the orange point. Well, what is it? The orange point, x prime is equal to 0 and y prime is equal to 0. Steady, yeah, that's right. So the both of them are frozen, and there's no growth of neither one nor the other. It is an equilibrium, right? So except it's not the equilibrium that we have seen with one variable at a time. Have two variables, and both of them are steady. So if the population starts at that point, it will stay there because there is no reason for it to leave. Okay, so we cannot conclude that the dynamics is cyclical. So you could try, and you must have done calculus 1 or 2 is dy dx and dx dy. Looking at rather than dy dx dt dy dt, you can look at the derivative of x with respect to y. So direct rather than dependence of x on y, x on t, you can go x on y or y on x. So that's also quite productive. Okay, so this is the vector field. So we are starting to learn and introduce new things based on this model because it pushes us toward new things. And so that the two differential equations, or rather two equations, are on the left. I could also write them in the form of a vector field. So what's on the right is the vector field. Okay, so so calculus 3. Who finished calculus 3 yet? Just about a lot. So then you know what a vector field is. It is once again a vector attached to every point. So on the field, which is a plane, and then every point has a vector attached to it. And so if your point xy, this is actually right here. So every point xy is associated with a vector uv, and then specifically if there's a formula, and we do have a formula, then that's for each xy, uv is computed and then plotted. Okay. So that's where we are, like this. So on xy, and from each xy, uv is computed, and then that arrow is plotted. That's a vector field. So it's how to do differential equations without actually solving it is something that we used to have in the form of a slope field. It is similar, but now this time we have arrows because these are vectors. And this is what a specific, it's not a simulation, right? But it is literally because I'm not doing the Euler method here. I just take the right hand side of my my system, and each point has a vector attached to it. Okay, you can see it clearly. Everything matches our qualitative description. Okay, some of the arrows are short, and so they seem like there's nothing happening, but you can surely see at the bottom we're going to the left, and then at the top we're going to the bottom to the right, to the left. On the left we're going down. You can kind of see that on the right we are trying to get up. So we also can see even there is somewhere stationary points here somewhere, maybe right here. And so it does seem to provide some kind of early motion around that equilibrium. So we're not trying to connect these arrows into curves. As you can see, they're just too long. If you remember what these are tangents. So you remember the theory of parameter curves. So if you have a curve, then every point will have a tangent added. Okay, so and then what we're supposed to do here is to somehow these tangent. It's not you don't put them together to create a curve, but rather your curve is supposed to follow all of these tangent lines somehow. Naturally, it's a challenge. Okay, but we're seeing the same as we're seeing the four types of behavior. The first two are number four is the most trivial. Number four, the freezing both of rabbits and foxes at zero level. They're in neither one or they don't even exist. So that we stay. That's not a stationary point, so probably worth mentioning. This is the number three stationary point where they're non-zero. So they just live in peace, even though they're eating each other. Nonetheless, they are not eating each other into oblivion. And then number one and number two, also the easy ones, are where there is exponential growth or exponential decay along the axis. So there's once again not especially important. Okay, so once again, it's an equilibrium. These two red black dots are the two equilibria. So 0, 0 in one case, this is 0, 0 right here. And gamma over delta, alpha over beta is that number 3 over here where once again everything is stationary. Okay. So the question that we might ask, and that's really what the now is all about, are the limit at infinity. Will we be doing the rotations? Will be spiraling in or spiraling out? So that's something that I hope you remember. So this is this is what I'm trying to do, exactly that. It's a more subtle analysis here, but nonetheless you can demonstrate fairly easily that the picture that I have here on the right is not possible. Neither this picture nor our qualitative analysis picture, this one, suggests something that it does not tell us that this is impossible. It's quite possible. Why not? Who is to tell that this is not the behavior that is produced? Is it possible to behavior to be like this, which means that what the rabbits are growing while the foxes are limited? So that would definitely indicate there is no any kind of spiraling. So that's actually another possibility that I want to put forward. So it's not necessarily spiraling in, out, or stationary. That's also a possibility, and we want to eliminate that possibility by qualitative analysis. And fortunately, here, as if you carefully look at our right-hand side equation, there is no flattening. There can be no flattening of the graph. So an asymptotic horizontal asymptotic behavior can only be possible when the derivative is getting towards zero. So we're growing. How do we flatten out? The y prime is 0. So this one is getting towards 0 or not? And the answer is no. Why not? Because it actually remains positive at all time above a certain number. Above a certain number, it never gets less than it. Which means that at the very least, it grows at least at the linear pace, and it means that it will penetrate every horizontal line it meets, and therefore, so once again, that we eliminate this kind of behavior as a possibility. And it's a big deal. So we now know that kind of a pack, and if it runs to infinity, it runs to infinity through kind of spiraling pattern. So we have demonstrated that the solution will go around the main equilibrium, but when it comes back, will it be closer to the center, farther, or will it come to the same exact location? What does the remember what the simulation told us? Well, these are three possibilities. Simulation, remember?
Spiral out.
It seemed to be spiraling out. What does that prove? Well, does it prove that it's not cyclic? It seems to be spiraling out like this. Okay, once again, made up points. Can we conclude that this is the behavior, roughly what the behavior is supposed to be like?
Actually, it'll reach the 0 points.
No. Yes, we cannot conclude that's true, but the reason is very simple. It's because it's approximate. Okay, so imagine that you're doing anything approximate, and then you ask yourself, will I hit the exact same spot? I'm supposed to come back and hit the exact same spot. If it's approximate, I will never hit that spot. So I cannot expect to detect the kind of a periodic pattern of behavior from simulation. If it's supposed to come back, it will only come back under the exact conditions when the solution is exact. When you approximate, will be either a bit higher or a bit lower. We can never possibly get, and if it does hit the exact spot, that's by accident. So we just don't have enough data. The simulation will not tell you anything about the periodicity because it requires the exact repetition of the same behavior, and we are approximate. So these are the three possibilities. As I said, the dots plotted will not eliminate neither one of the three possibilities, even though, so we saw this. This is what we saw, right? This one. But we cannot eliminate this. Can we eliminate this one? Maybe. I guess you can make a case that the spiraling in is not a possibility if on the simulation we see a spiraling out. Okay, but we cannot eliminate the periodic possibility. And long story short, it is actually periodic, turns out. So we cannot determine that it's periodic without solving the system of equation with an exact manner. And so that's what we're going to do. This is our system of differential equations. We forget about simulation and go on here with what amounts to get separation of variables, except in slightly different manner. Okay, so first of all, x positive, y positive. Okay, so that way we can divide by x and y. Okay, and that's exactly what we do. We express dt in terms of using the first equation and the second equation. So once again, these are two of my equations, and I remember that our derivatives are nothing but fractions. So I could actually, it's legitimate for me to solve for dt, and I do, and I have then dt as a function of dx and some expression in the denominator, and the same exact, once again, dt is expression with respect to dy and something in the denominator. So dt is eliminated, and then these two things are equal to each other, and that's a very nice example of related rates. So we speak of a rate of change of x and a rate of change of y, and they express in terms of x and y. So related rates, anyone remember what are they about? Related rates from calculus 1? It is actually very similar. So implicit relation, there is two quantities, okay, and they are depending on each other explicitly. So they are related, okay, and then what dx dt and dy dt are also related. Once again, not directly. You're not writing what dy dt is. But there is an equation for x and y. There is an equation for dx dt, dy. So that's a relation. Maybe it is. Remember, anybody remembers the problem of sliding ladder? A problem like that. Either sliding ladder x and y relate to each other, or it is blowing down of the balloon, and you're watching the volume versus the diameter or something like that. So once again, the third variable is hidden, and that's exactly where we are here. So separate variables. Turns out we can separate the variables. Look at it. So all x's are on the left, all y's are on the right, and so we can integrate as we have done before in exactly the same manner. Integrate with the one with respect to x, one with respect to y. We have division, and we have a couple of logarithms to be expected. Remember, ultimately, what's behind it is usual population growth, simply complicated by the interaction between them. But otherwise, it's still exponential growth or decay, which means that we can expect logarithm to be visible, and indeed that's what we have. Okay, plus c. So it is a one-family equation. Unfortunately, the bad news is that we did not get x in terms of y, x in terms of t, and y in terms of t. These are actually what we're after. The dynamics of x and y as a functions of time. That would give us the explicit solution being the parameter curve, and that's not the case. As you can see, as nice as it looks, this equation over here, there's no t here. So it is a relation between x and y. So can we get anything from it? We can because the relation between x and y, what does it give us? It gives us a curve. This will give us a curve in the plane, right? It is literally a relation to the gamma delta. Those alpha, beta, gamma delta are nothing but parameters of your model, so they are constant positive numbers. And then otherwise, we have x and y related to each other indirectly. By the way, you cannot solve for x or y here, unfortunately, once again. And C is just it gives you all the solutions that we want. So that's the equation. And long story short, I'll resume next time, but maybe I'll just show you the picture. Yeah, basically. Okay, basically. Okay, so see you. So I will not see you on Thursday. See you on this.